All right, so today we're going to be talking about Archimedes' piece, The Sand Reckoner, and his cattle problem, which might not make sense yet, but it's going to in a little bit. So, thanks to Claire, we don't have to completely go over Archimedes' history, but I'll give y'all some brief history about him and kind of like how it relates to us. So, he first proposed his cattle problem in 251 BC, right? So, that was obviously a long, long time ago. And it isn't actually exactly known when he wrote the Sand Reckoner. Although the person he was sending the Sand Reckoner to was King Gelon, and he was the ruler of Gela, an area in eastern Sicily. And Sicily is the island on the map to your right at the bottom of Italy. So, what are these problems? Well, the Sand Reckoner was a piece, and the goal was to figure out the upper bound for the number of grains of sand that could fit into the universe. And obviously, today the general consensus is that the universe is infinite, so there's no way to fit the number of grains of sand. But back then it wasn't, right? So there was an upper bound that could be fit technically. He was trying to argue that it wasn't infinite, and so the cattle problem was it was to figure out the number of cattle in a herd from the sun god with a number of like set restrictions. Again, that probably doesn't make any sense, but it will once we get to it. So, a bit on the Sand Reckoner. Aristarchus was the first documented to propose the idea of heliocentrism, and that's the idea that we follow today, where the sun is the center of the universe, right? So, in their terms, it was obviously not. We know that it's not now, but it's basically that the Earth and the other planets revolve around the sun, right? And as mentioned earlier, Archimedes is writing to King John, in which he pleads for him to accept the idea of heliocentrism for the argument, which we're going to see in a second here. So, again, the idea is to prove that there isn't an infinite amount of sand that could fit into the universe. So, his goal is to show that it's not infinite. So, he begins his argument by stating four assumptions critical to its proof. And I would advise everyone to pause and type in this link and follow along as I go through here. It's very long, it's very drawn out, and some of the proofs we're going to do are very complicated. So I would definitely advise pausing and going to check out that article. So the assumptions. Assumption number one is that the perimeter of the Earth is about 3 million stadia and not greater. And in the top right, you see a picture of what a stadia is in Greek. So that's kind of like your approximate assumption of what you have. So this was against the previous assumption that Earth had a perimeter of 300,000. So the second assumption is that the diameter of the Earth is greater than the diameter of the Moon, and the diameter of the Sun is greater than the diameter of the Earth. This all seems really obvious to us, but it wasn't very obvious back then. And it had been an idea that was developing, so there were a few astronomers that had proposed this before. So assumption number three, the diameter of the Sun is about 30 times the diameter of the Moon and not greater. So Eudoxus claimed that the Sun's diameter was about 9 times larger. His Archimedes' father actually said that it was 12 times, and Aristarchus claimed that the Sun had 18 times the diameter of the Moon. So it didn't line up with many of the people before him, but the proof that we're going to show later is going to help him, show that this is true. And a little fun fact at the bottom, it's actually 400 times larger, so obviously times have evolved. So assumption number four is that the diameter of the Sun is greater than the side of the Chiliagon inscribed in the greatest circle in the sphere of the universe, right? So back then, like I said, the universe wasn't infinite. So there was this idea that there was this sphere of fixed stars that was the universe. And so what that shape is actually 1,000 equal sides to form what almost exactly looks like a circle, but it's not. It's actually a shape with 1,000 sides. So this was based off of Aristarchus's finding that the Sun is about 1/720th of the circle that is the zodiac. And so this leads to the method in which Archimedes tries to find the angle subtended by the Sun with the eye as the Sun as the vertex. And you're going to see that in a second here with the picture in the top right. So to begin the proof, and this is a very long proof, so again, I would definitely advise anybody to follow along with the piece that I linked, along with definitely pausing the video here and there and referring to the picture above. So the first thing we're going to do is let a piece of paper be the plane that goes to the center of the Earth, Sun, and eye as soon as the sun rises above the horizon, right? So we're kind of taking our universe and we're just kind of cutting it down the middle to get a cross section of what it looks like. So we're gonna let this plane cut the Earth into a circle EHL and the sun into FKG. So this way the center of the Earth is C and the center of the Earth is O and the eye is E, right? So this plane also cuts the universe into the great circle AOB. So yeah. Next, we're going to draw two tangents from E to the circle FKG where the intersection points are P and Q. You can see that up here, here's P, here's Q. These tangents are coming out from here, and here, right? So do the same with point C and circle FKG where those intersection points now become F and G, right? Again, showing you up here and up here coming from C. We're going to let the segment CO meet the Earth and Sun at H and K respectively, right? So we're taking the center of our two circles, connecting them, and then the intersection with their circle is going to be those points H and K, as you can see. Also, we're going to let the segments CF and CG meet the great circle AOB at A and B, right? So you can see that above. Now we're going to produce the segments EO, OF, OG, OP, OQ, and AB. The intersection between AB and CO is now point M. You can see all these segments on this picture above here. Again, pause, check it out for a second, and then we will continue. So by all of this, we know that CO is greater than EO since the sun is just above the horizon, right? So, whether it's like 0.01 of an angle greater than, it has to be. So therefore, by that, angle PEC is going to be greater than FCG, right? So we can see that PEC right here is going to be greater than FCG. Right. We can also see that angle PEQ is greater than R over 200 and PEQ is less than 4 over 164, where R is a right angle. So that way, the right angle over 200 is going to be less than angle PEQ, and the right angle 160, and so like that's the kind of inequality statement there, and that's just by earlier statements. So by all of this, we now know that the angle FCG is also less than right angle over 164. So therefore, the chord AB subtends an arc of the great circle that is less than 1 over 656 of the circumference of that circle, right? So the segment AB has to be less than one side of the 656 sided polygon inscribed in that circle. So now the perimeter of any polygon inscribed in the great circle must be less than 44 over 7 of that segment CO. He cites right here the measurement of a circle, proposition 3. We saw this in earlier presentations. I linked it just in case. And so therefore, by this, the ratio of AB to CO is going to be less than 11 to 1148. And therefore, AB has to be less than the segment CO over 100. Like I said, this is a very long proof, and it's just a proof for one of the assumptions. So it's not critical that it's fully understood, but it is really important for this assumption that we prove this because it wasn't very much accepted. So since earlier we stated that CA equals CO, and since we can see that AM is perpendicular to CO and OF, that means OF is perpendicular to CA. Therefore, AM has to equal OF, right? So therefore, by earlier, we know that AB equals 2AM, which equals the diameter of the sun. And then also, since our segment AB is less than CO over 100, the diameter of the sun is less than CO over 100. That's just by transitivity. So that the diameter of the Earth is less than CO over 100 by assumption 2, right? So there we have assumption 2 and 4. So by construction, we now know that CH plus OK is less than CO over 100. Again, that's just by transitivity, taking things from earlier and aligning them now. So by that, we know that HK has to be greater than 99 times CO over 100. So in other words, there's just a ratio, right? So CO to HK is less than 100 to a 99. Also, by the same logic, we know that CO is greater than CF and HK is less than EQ. Therefore, CF to EQ has to be less than 100 to 99. Again, that's just transitivity and ratios by earlier knowledge. So to finish up the proof, we're going to turn our attention to the triangle CFO and EQO. I know the picture is kind of hard to see, but like here's CFO right here. And then we're going to have triangle EQO, which we know E is here, and that's going to go to tangent Q, and then O is right there, right? So we're looking at these two triangles. So it's seen that OF equals OQ. That's just by construction. But since EO has to be less than CO, as we had seen earlier in our statement, EQ has to be less than CF, right? Since CO and CF. Therefore, the ratio of CO to EO is less than the angle OEQ to the angle OCF, which has to be less than CF to EQ. And again, I know this is a lot, but it's going to make sense as we wrap it up and we kind of understand why he's making these assumptions and why these are important. So if we double our angles, which seems random right now, but we can see that the angle PEQ, the ratio between PEQ and ACB is less than the ratio of CF to EQ, which is also less than 199 as stated earlier, right? However, by hypothesis, our angle PEQ has to be greater than the right angle over 200 as we had seen earlier. Therefore, the angle ACB has to be greater than 99 times that right angle over 20,000, which is going to be greater than the right angle over 203. So by this, the arc AB is greater than 1 over 812th of the circumference of the great circle AOB, right? And again, the great circle being the universe. So therefore, AB has to be greater than one side of the chiliagon, and therefore AB must be equal to the diameter of the sun. And that lets us continue with the rest of the problem. So there are subproofs now that we have to prove that isn't the proof of an assumption to continue. So we want to prove that the diameter of the universe is less than 10,000 times the diameter of the Earth. Also, that the diameter of the universe is less than 10 billion stadia. It seems really random, and it did to me too, but once we get further along, you'll completely understand like why these numbers like are here and why he chose them. It's kind of like that upper bound idea. So the notation I'm going to use here is going to be d sub u is going to be diameter of the universe, and then d sub s is going to be diameter of the sun, and so on. So like dE is Earth, and then dm is moon, right? So by assumption 3, we know that the diameter of the sun is not going to be greater than 30 times the diameter of the moon. Also by assumption 2, we know that diameter of the Earth is greater than the diameter of the moon. These are all by construction. So by this assumption and transitivity, we know that the diameter of the sun is less than 30 times the diameter of the Earth. We know that's not true nowadays, but this was, again, not known knowledge. So by the last proposition, the diameter of the sun is greater than one side of the chiliagon inscribed in the great circle, such that the perimeter of the chiliagon is less than 1,000 times the diameter of the sun, which is less than 30,000 times the diameter of the Earth. That just comes up from up here, right? So multiplying it by 1,000, right? Since there's 1,000 sides. So the perimeter of any polygon with 6 plus sides inscribed in a circle is greater than that of the inscribed regular hexagon and greater than 3 times the diameter. Taking this knowledge and relating it to our proof, the diameter of the chiliagon is greater than 3 times the diameter of the universe, right? So it follows that the diameter of the universe is less than 10,000 times the diameter of the Earth. That's just from previous knowledge and transitivity. Therefore, the perimeter of the Earth is not greater than the length of 3 million stadia by assumption 1. Also, the perimeter of the Earth is greater than 3 times the diameter of the Earth. Right. So by these facts, the diameter of the Earth has to be less than 1 million stadia, and therefore the diameter of the universe has to be less than 10 billion stadia by construction. And again, taking like right here, multiplying it by 1 million, you're going to get that. So now that we know that, I'm going to kind of go on a little tangent and kind of explain orders and periods. It's going to seem a bit off topic, but it's going to make sense right at the end, right before we get to this upper bound. So The Greeks had names for numbers up to a myriad, right, which is 10,000. These numbers could go up from, they could go up to a myriad myriads, right? So 100 million, which is going to be 10,000 times 10,000. Archimedes called these numbers the first order of numbers. Then numbers of second order go from 100 million to 100 million squared. This pattern goes up to 100 millionth order of numbers, which Archimedes calls p, right? So numbers from 1 to 100 million are called the first period of numbers. This is all just like pure definitions and pure like construction to Archimedes. So we're going to see how it kind of relates in a second here. So the first order of the second period are numbers from p to 100 million p. The second order of the second period is going to be 100 million squared times p. And this pattern is continued until we reach the 100 millionth order of the second period, which is going to be noted 100 million to the 100 millionth power times p. So then we can go even further to where p squared is the first order of the third period, which is beyond even like what anybody could have comprehended back then. And so this follows the exact same pattern of periods and numbers and orders of the ones prior. So this pattern is continued until we can reach the 100 millionth order of the 100 millionth period, which is going to be p to the 100 million. So this is where we're going to get to assumption 5. I know that kind of seemed all really random, but we're going to see how it relates in just a second here. So the assumption that Archimedes makes is that suppose a quantity of sand no larger than the poppy seed contains no more than 10,000 grains of sand. Nobody knows where he got that from. Nobody knows why he assumes that. It's probably not true, but that's just where we're going from here. So then we're going to assume that the diameter of a poppy seed is no more than a 40th of a finger breadth, which is just like the width of your finger, like here, right? So you could fit 40 poppy seeds across your finger, and there's 10,000 grains of sand in a poppy seed. So by assumption 5, and the fact that spheres are to one another in the triplicate ratio of their diameters, the sphere with a diameter of 1 finger width is not greater than 64,000 poppy seeds. That's, if you took the width of your finger and used that as the diameter of a sphere, you're going to be able to fit 64,000 poppy seeds in that. And by earlier logic, we know that 64,000 poppy seeds, 640 million grains of sand. So this number can also be written as 6 units of the second order plus 40 million units of the first order. And this is going to be important as the next slide, so you can see, right? So we know that the universe does not have the diameter of a finger width, right? So we're just going to, what he does is he just takes that sphere and he just makes it larger and larger and larger. And it becomes so large that no universe to him could fit that number. So at the bottom of the picture on the right, we can see that the 10 billion stadia can fit 1,000 units of the 7th order of sand. However, by the proof at the beginning, the diameter of the universe cannot be greater than those 10 billion stadia as proved earlier, right? So it almost seems as if we've hit an upper bound of sand, right? But we only know it in stadia. And this is why that number construction from earlier becomes so important. So when you get to the final part of the proof, you're going to get that upper ground, right? So kind of resetting what we know, by hypothesis, the Earth to the universe is equal to the universe to the number of fixed stars, right? And also the diameter of the universe is less than the diameter of 10,000 Earths. Therefore, by transitivity, the diameter of the number of fixed stars is less than 10,000 Earths. So the sphere of fixed stars is less than 10,000 cubed universes. That goes by that triplicate ratio he was talking about earlier. So in the end, Archimedes claims that the number of grains of sand that are contained in the universe, in the sphere of stars, which is the universe, goes as follows, right? So you have 10,000 cubed times 1,000 units of the 7th order, which is going to be less than 13th terms of series times the 52nd term of series, which is less than the 64th term of series, which is less than 10 to the 7th, or 10 million units of 8th order numbers. And that is the upper limit of how much sand could fit in Archimedes' universe. So in conclusion, this is what he says. I conceive that these things, King Jelen, will appear incredible to the great majority of people who have not studied mathematics, but that to those who are conversant therewith and have given thought to the question of the distances and sizes of and the earth, the sun and moon, and the whole universe, that proof will carry conviction. And it was for this reason that I thought the subject would be not inappropriate for your consideration. So he has proved to the king that the universe isn't technically infinite, and there is a number of grain of sand that you could fit in the universe. So that was very long. So now we're going to get to the easier bit. I say easier, but it's really not, and you'll see why. But so Archimedes' cattle problem. So this exhibits perfectly how a simple set of equations can create an absolute mess of a solution. There are two parts of the problem, both of which took a really long time to complete. So this is the overview. You can read the part on the left, but the picture on the right is so much easier to understand. Pretty much what it is that a sun god has a herd of cows and bulls, right? So, and then it kind of follows this equation where white bulls equals 1/2 plus 1/3 black bulls plus yellow bulls, and so on. So the idea is to solve the system of equations, right? And it wasn't too hard until the second part comes. So here we can see that there's 7, parts. There's, 7 different equations with 8 unknowns. But then this part comes in. He says that the white bulls plus the black bulls has to equal a square number, which is going to be 1, 2, 4, 9, 16. We know what the square numbers are, which isn't terrible. But then you get to the dappled bulls plus the yellow bulls equals a triangular number. And as you can see on the right here, so the triangular numbers are going to be 1, 3, 6, 10, 15. And that's because, this is 1. Then if you add it, you have 3. Then if you add all of them, you have 6, right? And that caused a lot of problems. So the first part isn't too bad. So it didn't take too long, but to get all 9 conditions, it wasn't solved until 1880. And it wasn't even fully solved because he only got the first 3 digits of what the number would be, which is going to be 776. And that was by Carl Ernst August Amthor. So obviously it's going to be a huge number, as you can see, because it's going to be 776 plus 206,542 digits. So yeah. So the first thing we had is this system of equations, which isn't hard to solve. It has an infinite number of solutions, but the lowest we can get is to where the black bulls is 7.4 million, the white bulls is 10.3 million, and so forth and so on. I think we can all solve a system of equations here, right? And that's just the lowest one. So that's going to be a total of 50 million cattle, which is a lot, but it gets a lot worse. So for parts 8 and 9, the way they solved it was the Pell equation, which is going to be x squared minus ny squared is equal to 1. And that's going to be a lot of resemblance of a hyperbola. So I'm going to provide the link to the article which talks about how he got to n equals w to the 460 58th power times j minus w to the negative 4,658th power times j, all squared, all over 4657 times 79072. I'm going to link it. It is 6 pages long. It would probably take us hours to get through. However, that number equals this part right here, 7.76 times 10 to the 544th power, which is how we got to 776, but he had no idea what those last numbers would be, right? So kind of running through this to get part 8, we know that b plus w must be a square number such that using the Pell equation, we're going to get b plus w equals 7.4 million k plus 10.3 million k, which we got actually from these numbers here, b and w, right, at the left, right over here. And then, so which is going to equal 2 squared times 3 times 11 times 29 times 4657. We see that number over right here. And then we can see that it's just plus 1 right here. Times k, then we can set k equal to that number, q squared, where q is some integer, and solve for it to get to our answer. All right, so it's not too bad. It's just that 6-page document that I go through and understand it. So Part 9 was a lot worse because it's that triangular, right? So we know d plus y must be a triangular number such that using the Pell equation, we're going to get d plus y equals t squared plus t all over 2, right? And then we're going to solve for t to get this right here, right? So finally, we substitute the values of d and y and k in terms of the Pell equation to find a value for q squared to get this right down here, right? Let's let it disappear so we can actually see it. Great. Which is going to be p squared minus 4 times 609 times 7766 times 4657 squared times q squared is going to equal 1. Again, that's all outlined on how we got there in the document that I linked. You can just pause, type it in, and yeah, it would just take hours for me to get through on here. So the answer, what is the final answer to solve all 9 equations? It wasn't done until 1965, which is 2,000 years after this problem was first introduced, and it was done through a supercomputer through code. Nobody, came to solve it. Nobody's going to come to solve, 206,000 digits. And it came out to be 42 pages of numbers, which looks a lot of something like this right here, right? So that was the answer to the cattle problem. And that's it. There were the 2 answers for his problems. Thank you.